there is n points in x0 to xn minus 1, and its values of the function at those points are given. Y is minus 1. So Lagrange interpolation. So we can get values of function, approximate function. Well, basically can't get accurately because we really have only finite number of points, but we can get approximate function. I call it P of x. Okay? And that was product. So that it was sum of okay. So what was it? The sum Lj yj, and Lj is function of x. Right? So Lj is a polynomial, and Lj was product x minus xi, xj minus xi. Yes, that was the product. So with this, I can get the value of the function at any place, but it's approximate value. It's not the real value. And if you use large enough number of points, then you can get reasonably good approximation. So we get first order polynomial, second order, third order. Depends on how many points you choose. The easiest is 2 points, which is linear interpolation. Okay, so it's clear to everyone. Now we can do this to 2 dimensions. So we have 2 dimensions of function. So for example, temperature on a surface on a plate. So that function will be f x comma y. But again, when I make the measurement, I will only make the measurement at finite number of points. So for this class, let's assume that I have a grid which is rectangular grid. They need not be uniform. Here also, this xj minus xi is not. They are not equal for each neighboring points, right? I didn't assume uniform separation between the points. Here also, but I assume that this is not same as that, this is not same as this, but I assume a square mesh, a rectangular mesh. So delta xi are not equals. So this also can be called delta xi. Okay, so how do I interpolate? How do I derive a formula for this? So derivation for this formula is on similar lines. So let's first derive along x. So I will say, well, I'll fix yj. So I'm going to use a slightly different notation in this. These indices will be j and these indices will be y. So my function is yi comma j. Here j was the running here j was the running index, but I am going to use j for y coordinate and I for x coordinate. Change of notation. So for a given j in this direction, I can do interpolation. So formula. So let's first fix j. So my polynomial p x comma so this is of x. I'm going to put that I here in a minute. So this function. So, but this is so. I will use y I comma j. But now I am summing over all i's. So remember I is, so I am basically fixing here I equal to 0, I equal to 1, I equal to 2 like this, going down like this. Now I comma j. Now this will depend on I prime. No, this is no, right now this is sum. This is sum. So I am summing over I, no product. So this is error. So this sum over I. Now li will depend on points here. So Li of x is product, I just write this x minus xi, but I do not use j because j is for y coordinate. So xi prime, I am use I prime minus xi, I prime. So I prime is the index, running index in that direction. So okay, so this is going to give me interpolated values on a given line, horizontal line. Now for every j I can write these functions. So I interpolate along x, and my y of course are fixed. They are basically those along the lines which are given to you. Now I can interpolate along that direction. So suppose somebody wants value of the function here, which is neither on the horizontal line nor on the vertical line. So what do? So I draw a dashed line, and now I know the value of the function here by this formula, because that corresponds to this particular j. Value of the function here, here, all these values. Now interpolate along y. Okay, so that's the idea. So I want now, so we can call it p prime, this intermediate. It's not the full function I want. I want to be able to interpolate at any point in between. So this is a point x. So pxy will be now. So I'll use this function to interpolate sum p prime x by j y I comma j. Pxy, sorry, pxy. So this is my what I am doing. Lij xy yij. So this is what is my interest. Now this Lij will be including both x and y variables. So Lij, there are two sums. Product x minus I prime, and for the y, I have to do for the y. Product, so this I prime, j prime, y minus y. So you do in two steps. So this is a formula. This will give you the interpolated value at any xy in the domain. Okay. You can generalize it to 3 dimension or any dimension in fact. So for 3 dimension I will have this ijk. 3 dimension. So you will have 3 products. So we do it like this. It's very useful. Many times we need to work with functions in 2D, 3D. This sums up Lagrange polynomial interpolation. Now there are many more. In fact, there is something called using Hermite's polynomial. The disadvantage of this scheme is that suppose I have a set of points. Then I can do Lagrange interpolation here, and then Lagrange interpolation in 2 segments. I can do, let's say I have n minus 1 points and m minus 1 points here. Now in all this stuff I needed value only at the value of the function at yj's. I didn't use a derivative. So one may say, well, I'll give you function as well as derivative. then I can do, I need with, okay, so I think this part is a different idea. This part is a different idea. So here I'll have points, and I give you the derivative as well as the value of the function. Then with n points I can get 2n minus 1 order polynomial. So I'll have 2n coefficients. Okay. But that's a bit of more mathematics, so I'll skip that part. So I'll give you the notes which has some details, with maybe there are some errors, typographical errors, but that has some details. The reference book for this is Perzizer. Is there in the website, the full detail is also, some copies are there in the library. So a Hermite polynomial is described there. If you are interested, you can look at it. Now I am going to work out another one called splines. So let me just, before going to spline, I will make another remark. We can do piecewise. There are second piece. So I can do interpolation of maybe 5 points here, then another 4 points here, 3 points here. So it is possible to do things like this. So let's say I have 100 points. So you are not going to work with 100 order polynomial. Okay, that's too clumsy, and so you work with piecewise. In fact, the idea for spline is goes in the same direction. So splines. So splines are objects which are smooth. In fact, if you done engineering drawing, those plastic curves, they're splines. So in fact, we can get any continuous function by those splines. And if you should use some drawing packages, you can just move it around, and the curves takes very smooth functions. So there are, of course, lots of splines, many types of splines. I will focus only on cubic order splines. This is one of the very popular interpolation package used in graphics, heavily used in graphics. So graphics, you don't have values at all the points, but you can interpolate pretty good. So GPU will be doing a lot of this stuff. So if you're playing games, the GPU is really working hard to. You will have pixel, and it will do some interpolation to give you a better image. Okay. So the idea of spline is, so I have again n minus 1 has 0 to n points, but I want to construct a function f passing through these points, which follows the equation of a beam. I don't know how many of you know the equation of a beam, hanging beam. So this is a beam. Right now it is stable. The beam from one side of the wall to other side of the wall. Or rod, just so beam is, we can have a rod attached like this. So it is that. So this is called beam. You can have beam where it is attached to one side, and it will. Okay. So this is called beam. Now, so I am going to use construct a function, beam function, which will go through these points. And each point there is certain load. So the idea is, in fact, it comes from civil engineering. So I have a function f. So equation of the beam is d4x, dx4, and the coefficient in front is f. This is equation of the beam. Okay, so the fourth order. It's one of the few equations which involves fourth order. Now these are elasticity coefficient and moment of inertia. Okay, so ignore this. Now this function is reasonably smooth. It's fourth order, so it's smooth. Higher order function is smoother. Now we will assume that at each point, given point, so these points are called nodes. At each point there is a weight. and because of the weight, it will wobbly. It will look wobbly. So we construct f given this condition. So if it's fourth, so its derivation is the equations are a bit lengthy, but the idea is quite simple. Now I am going to demand something on f. Then, so what are the things I demand on f? That this f should pass through all the points. Natural law. So f then the derivative is continuous across. So at each point I just have the derivatives, and derivative also is continuous. So the slopes are equal from both the sides. So f prime x left it's a differentiable function. One more thing. Yeah? Sorry? So E is the elasticity coefficient and I is the moment of inertia of the beam. We don't need to worry about it. This is the equation. I will use it. I am not going to specify this. Okay, it will become clear in a minute. We don't need. This is fitting. I mean, I am borrowing the idea, but I am not using really the beam. Okay. In fact, we also demand the second derivative. Second derivative is also continuous. Okay, first order, second derivative, and the curve is. These are things which are demanded for all these functions. So now how do I construct the function? Now you've done quantum mechanics with delta function, no? There's one wave function solution. So what can you say about this function? So since fourth order, so this is a delta function at each node. Is a point mass which is hanging. So f is of the form delta x minus xi fi is a number. I will again not specify fi. It will be coming from what I am going to demanding by construction. So what can you say about the fourth order derivative is a delta function at those points. So what can you say about the third order derivative? Third order is step function. Okay? So third order will be step function. So it is constant to the left and constant to the right of the each node. So second order derivative must be linear. Okay, the second order derivative is linear. So I have this set of points. So I am going to focus on 3 points: I minus 1, I, and I plus 1. So let's write it here. I minus 1. So if f double prime, not f, a double prime is linear in x. You are happy with it? So we will use the Lagrange interpolation formula to get the value of the f double prime between any interval. It's linear. So f double prime of x, let's say the interval I minus 1 to r, I to I plus 1, I to I plus 1. I will say this is a linear function. Each piece is linear function because it's a delta function. It just follows. So I will use Lagrange interpolation to write down the function f double prime, assuming that I know the f double prime at each point. Okay. So in fact, So step 1 is, suppose you know f double prime at each point, you can write down piecewise linear functions. Okay. So what is this? By Lagrange interpolation. The formula is linear interpolation x I plus 1 minus x divided by. Okay, so this interval. Similarly, you can write for this interval as well. So for every interval, you have a double prime, which is linear. Now, if you have the function, then I can get fx. So integrate this twice. But we demand one more point, one more condition, that fx must pass through yi and ya, all yi. If you put that condition, it's a bit of algebra, so we'll have two unknown coefficients. Now, two unknown coefficients, how are they fixed? They're fixed that at fi the value of function is yi, and here is yi plus 1. So you have this, and just integrate twice. Say that fxi is yi, and fxi plus 1 is yi plus 1. So I will not do the algebra, and I just write down the function. This one I write fully, even though I'll share these notes, but let me write this. Okay, so this is pretty lengthy expression, but this is a cubic ordered polynomial for x. Okay, so that's what I said. My function f will be cubic ordered, and that comes from this equation. Oh, great. So hi is this xi plus 1 minus xi gap. And this will be hi minus 1. Now I will only sketch the next part. So you have to write down function. So this is f of x, I already wrote. You can also write f of x for this part. Now once we have f of x at both sides, I demand that my derivative is continuous. So I can compute the derivative here from both the sides. And I demand the derivative from the left is same as derivative to the right, and I'll get a condition. And if you do the algebra correctly, you are welcome to do it. If you do the algebra correctly, you will get equation which looks like, which is quite easy equation in fact. Hi minus 1 by 6 plus 1/3 equals the equation. Okay, so this by setting the derivatives from both the sides equal. So how many equations will I get like this? I can set it up only from the intermediate points. I can't set up at the endpoints. Right? So n minus 2. So I get n minus 2 equations. These are known. Yi and His are known. What is not known is the second derivatives. So in fact I assume that, well, I said that suppose somebody gives me a second derivative, then I can set it up. But then now I say, well, I don't give you second derivative, you have to figure it out. So I got n minus 2 equations, and how many unknowns? I got n of the second derivatives unknown. They are unknowns. So I can't figure out right now, but I can now set up few extra conditions. Now, so I set up some conditions. One condition would be the derivative at both the ends are 0, double derivative. So very simple condition is that a double prime at 0, 0 is 0, a double prime, and this is called free beam. If you have done this beam equation, so at both the ends is free. So you can hold it in the middle somewhere. You can put two columns. The beam is held, but at the end there is no stress. Okay. So this is called free beam, free condition. So I give you two conditions. So now I have n equations, and I can figure out. Well, I already gave you two of them, but n minus 2 can be figured out by this equation. There are some other conditions called, well, one thing is periodic boundary condition. So it goes in a circle. Periodic means it goes in a circle. So we demand that a12 prime 0. Well, this is slightly tricky. Huh? So this is for the double derivative. It's not for the function. So of course we demand for the function that y0 is same as yn minus 1. That is continuity for periodic. So 0 is same as n minus 1. So these are together. So n minus 1 basically lies on not n minus 1. That will be n. This will be n. This is n minus 1. 0 is same as n. We don't specify n. No. Periodic of the function should imply, periodic should imply that n minus 1 should be equal to. Okay, so I am not certain that I need this n minus 1 here or n here. I am not 100% sure. So I can tell you what is for the double derivative. Okay, so double derivative demand. A double prime x. So I will clarify this in the next class. So double derivative for the periodic boundary condition is a double prime x n minus 2 and a double prime is periodic. And we can also have some other conditions. So this is called parabolic runout. So that's that condition. Third condition is f dot prime 0. So since the double derivative is equal at two consecutive points, my function will be parabolic, f dot derivative is constant, so it's parabolic near the end. Now these two can be combined to call cantilever end. Lambda lambda lies between 0 and 1. And this is called cantilever condition, cantilever end. And these are 4 popular conditions. So with this you can close and you can find out f dot prime. Once you know f dot prime, then you can find out f. And it's piecewise cubic. It demands that its function is continuous. Its first derivative is continuous, and also second derivative also same. So it's continuous. So it's a very good interpolating function. In graphics, it's highly used. Now I will just show you how to do it in Python. So Python has this built-in function for doing spline. But before that, maybe we can just work out the example by hand. So this part I will leave it as homework, but I'll just sketch what do you do for the 4 points I discussed in the class. 1 over x, the function is 1 by x. So my function is 1 over x. I gave you this, and they are at points 2 to 4, 2 to 5. So now we worked out in the last class with Lagrange interpolation. So we can do the same thing with splines. So how should we proceed? So I need to write down this equation. I just erased it. This equation. I should not erase that equation. But if you just do his homework, here hi is the same for all of them, is equal to 1. Right? Hi is the difference between two consecutive x, that's 1. So now this equation, the condition equation for f dot prime, I can figure out for these 2 points, intermediate points. And these come out to be, I'll just write down one of them, 2/3. So these are double relative at 0.1. So this is 0.1, this is 0. Equal to the right hand side, that was yi plus 1, yi minus 1. So you write it out, you will get 2 equations, there are 2 intermediate points. Now for the end points, I will say that you use free boundary condition. Okay, so you'll get all the 4 f dot prime, and from that you construct this fx and plot it. And how good does it fit with 1 by x? Okay, so that homework is clear. Okay, now let's use Python's spline function. So, okay, now before going to Python spline, let me also, I have 10 minutes, so just want to make a remark. So let's relook at this part. So it had f dot prime xi minus 1 plus f dot prime xi equal to right hand side, which was given to you. Now there is n minus 1 on it. So you can write this in as a matrix. Correct? These are unknowns. So these become a matrix. In fact, the first entry will be f dot prime 0. Here, how will the matrix look like? This part? 3 entries. So this is called tridiagonal matrix. Elements here, elements here. Okay. So we can write this equation in terms of matrix. So this is tridiagonal matrix. And we can solve it. Now this part I will do towards later part of the course, how to solve tridiagonal. So you will find that the computational physics, they are all connected. To do the interpolation, I need to know how to solve matrices. Okay, so this part we will do later. Now, so full matrix algebra will be done later part of the course. So let's quickly look at the, this again looks tiny. So interpolate, we can do one interpolation. So this is one interpolation. So this part of SciPy, scientific Python, and the whole package is, so within SciPy there is a package called interpolate. And within interpolate we have various functions. So I have to say interpolate dot inter key 1D. So interpolate 1D. So this interpolates 1D. So so this is a range. It's like range function, but it's for real function. So it starts from 2, it goes up to 5 with an interval of 1 to 5. Okay. So this by x. So interpolate yp will be result coming from this function. It will write in y. I want to plot it. So I create a new function y interpolate 1D, and basically I put in a loop and I just copy everything in that function. There may be a shortcut, but I just did that at some point. So the answer is here in white. So this is going to do interpolation, 1D interpolation at any point you give you give to the function. And where are the points I have given? I have given this x. Actually, yeah. So no. Okay, now I get it. So yp is a function. Yp is some kind of thing generated by Python. Now you have to give xp as an argument to yp. Yp is not an array. Yp will have polynomial. In fact, we construct the polynomial. Is that part clear to you? So yp is not an array. It is some kind of, it has all this parameters which you don't need to worry about it. It does. Now yp will act like a function and xp is an argument. So this will give you a value which is appended to interpolate 1D. Okay? So my final answer interpolate 1D is array, which are values of the function. The value is at x equal to this array. So I need to plot x versus y interpolate 1D. Now this for interpolate 1D, which is not a very good function, it's a linear interpolation. We'll just see in a minute. Now for spline, so you have to focus on this part, it's pretty similar to this. So we give the x array and y array. So x array and y array are here, 2, 3, 4, 5, and y array is this. You give it here. So it again gives some parameters. It makes like a function tck. Set a parameter. Now tck will become an argument for spline evaluate. So whatever x you want to compute the value of the function, interpolated function, we just pass on this xp. So xp, you see this is loop for all xp lying in x. For loop. So I give the argument xp and set up parameters obtained by this function. Spline is represented here. So tck becomes the argument of this and will compute. And will put in spline append. So I am just adding this to one by one. And so my result will be in y spline, which is created by me. Y spline is not system function, but created by me. So we have to do this. So let's run it quickly. So it make plots. Some of you are still struggling with this CD stuff. Okay, so run spline. this is a plot. So my function is that pentagon 1 by x. Spline is doing a very good job. It's cubic. So cubic is good. This is interpolate 1D, which is linear. It's not doing a good job. So spline is easy to use. So if you just pay attention, you should be able to do it. And the errors are plotted here. So error in interpolate 1D is quite large. The spline error is quite small, less than 0.005. A double prime xi plus hi by 6 f double prime xi plus 1. So this was right hand side. So yi is right. So that was yi plus 1 by hi minus yi hi minus 1. So there were n minus 2 equations. We do it for, we skip this point and this point. So there are n minus 2 equations. But I have n unknowns, f double primes. So we need to assume something. So if we assume periodic, then these 2 points are the same. Okay, so it's like in a circle. So 0, 1, 2 like this, and this becomes n minus 1. So effectively we have one less point. So we have one less point, then we need one less condition. So it's already n minus 2. So I just need to minus the double derivative here. So what we want is a double prime x0 x n minus 1. Well, they're same point, but you have to take double derivative from the left and from the right, and that will that is what we are assuming in this. So that will give you n minus 1 conditions, and we have n minus 1 unknowns, and you can solve it. The other conditions, parabolic runout. Parabolic runout has, so let me just finish it off. So these 2 points have same double derivative, and these 2 points have same double derivative. So we assume that the double derivative here is same as here, double derivative is same as here. So it's parabolic in this regime. Double derivative is constant. So this is periodic, this is parabolic runout, and then free end. Free end, these 2 points have 0 double derivative. A double prime is 0 here, and there is something called cantilever end. Cantilever end. So there I assume that a double prime x0 is lambda a double prime x1. Okay, so except the periodic case, we need 2 conditions. For periodic case, we need only 1 condition. Okay, so and they are solved using solving the tridiagonal matrix, which we will cover later part of the course. For you right now, use 4 points and do the homework. With 4 points, you need only to solve 2 equations. Okay, so please do the homework. So piecewise cubic, and its first derivative and second derivatives are continuous. That is a condition we imposed. So curves are quite smooth. Advantage of spline over Lagrange polynomial is that for Lagrange polynomial, if I want to fit with n points, I will get nth order polynomial, no, or n minus 1th order polynomial, and there will be a lot of oscillations. Higher order polynomials have oscillations, and that's not nice. If you have, in fact, it's impractical. If you have n equal to 50, so 50th order polynomial is not a good thing. So we want smooth function, and it is cubic in each piece. So it works quite alright. You can do higher order spline, but this is very popular. So is that clear? And also for estimate, the zeta for Lagrange polynomial lies between first point and the last point. Okay, so zeta is between first point and the last point. So then you have to estimate max value of f prime f nth derivative of zeta. So you have to find the minimum and maximum between the two.